Hi everyone, my name is Mher Baburyan and welcome to my presentation of my capstone, which is about design and development of mechanical transmission experiments. My supervisor is Sarkis Zeytunyan and advisor is Arman Asatran. This is the table of content. I will briefly talk about the project requirements, what is transmission applications, educational values that they hold, fundamental concept, divergence. I'll briefly talk about the existing experiments that AUA acquired from Edibon. Then I'll talk about my new experiments and then the future work. So the project requirement is to design experiments that will complement the already existing Edibon setup, help students learn the basics of mechanical transmission by doing hands-on experiments where they can compare theory with practice, and also development of user manuals to guide students. So what is transmission? Mechanical transmission is a system that transfers power from an input source, changing its speed, direction, torque, or other things to meet mechanical needs. We are all familiar with them, and one of the best examples is the chain drive of a bicycle that everyone knows. So applications, mechanical transmissions are used everywhere, starting from bikes to cars to heavy industrial machinery. And educational values. Academic integration. These setups can be incorporated into different courses throughout the engineering curriculum to learn about every aspect of it. Then enhanced learning through implementation. Students can use these designs in their courses to learn how they work, how to design them not in theory but in practice, and also to prepare students for the rise of robotics. As we have seen today, some exceptional presentation from Daniel. The increase in robotics will require many transmissions units and also people who know how they work and how to design them. Then fundamental concepts. The most important fundamental concepts are speed reduction, which is basically shows by what factor the speed gets reduced. Mechanical advantage, which shows how much the input torque gets increased. And in theory, both mechanical advantage and speed reduction are equal, meaning that if the speed gets reduced by the factor of 6, then the mechanical advantage, the input power will be multiplied by 6. But as in real life, there are losses due to friction or misalignments. It is not always the correct value, and efficiency shows how much of that input power goes to actually turning the output shaft rather than being lost in friction or misalignments. And selecting transmission involves trade-offs between reduction ratio, torque output, efficiency, size, and etc. And different transmission units are used in different spaces as to meet specific goals. And the review of already existing setups from Metipon, they include belt drive, chain drive, gears, bevel gears, worm drive, and universal transmissions. Now into the new setup. The first setup is planetary gear transmission, and they are used everywhere where small space and efficiency matter. On the left side, you can see a picture of a planetary gear transmission used in a bike, and the other picture is a planetary gear transmission used in a mining rig. And they consist of sun gear, planetary gears that are mounted on a planet carrier, and a ring gear. There are three main configurations: fixed ring, fixed sun, and fixed planet carrier. And in my configuration, I used fixed ring. It is the most used one. Here you can see the motion of a planetary gear transmission. The planetary gears roll inside the fixed ring, causing the planet carrier to rotate slower than the sun gear. In the middle, in the center, you can see the sun gear, which rotates around its axis. Then you can see three planet gears that not only revolve around their axis but also around the sun gear, hence the names, sun as it is in the center and planets as they revolve around the sun, and also a formula of the reduction ratio. Then my model consists of sun gear with 16 teeth, 3 planet gears, fixed ring gear with 80 teeth, planet carrier, 2 bearings and 2 pulleys, and the reduction ratio is 6. Here you can see the exploded view of my planetary gear transmission, and also the real build. Here you can see it. The real build. We ran some ideal case simulations without friction, and this just shows that our calculations were correct. The blue line that you see is the angular speed of the input shaft, and the red line is the angular speed of the output shaft. And if we see the values, the reduction ratio is 6. So how does the experiment go? There are 2 experiments. The first experiment is clarifying everything, calculating the reduction ratio with a formula, then rotating the input pulley and counting turns of the output pulley. So if the reduction ratio is 6, the input pulley must rotate exactly 6 times for the output pulley to rotate exactly once. Then, after clarification, the second experiment will be done, which is about calculating the efficiency of the planetary gear transmission, which is about hanging fixed weights on the output pulley, then gradually adding weights on the input pulley till the weights on the output pulley rise, then filling the table and calculating everything. This is how the experiment will go. And this is the table that they will have to fill. This is the actual results from the experiments that I did. And also the efficiency versus load graph. And also the difference between real and ideal input weights. There is a lot of difference, and due to some friction and misalignments in the system, which was actually expected. But sometimes you don't need efficiency that much. You just require high reduction ratios, and this is achieved by 2-stage planetary gears that you can see. The example of this is here. And it is basically 2 planetary gear transmissions that are connected in series. And there are 2 configurations, common ring and the one that has separate rings, and the reduction ratio is just the multiplication of each stage. Here you can see the motion of a 2-stage planetary gear transmission. At the back you can see relatively fast input, and at the front you can see relatively slow output. And this is the design. It consists of sun gear with 16 teeth, 6 planet gears, fixed ring with 80 teeth, planet carrier with gear teeth, planet carrier, 2 bearings, 2 pulleys, and the reduction ratio is 36. And this is a very important model, a component of the 2-stage planetary gear. This component is responsible for connecting 2 separate stages together and making it work as a single component. And also the exploded view of the transmission, and also the real build. As we also ran some ideal case simulations, and it is everything that is the same. Blue one is the angular speed of the input, and the red one is the output one. And here is the table that we got from our experiments. Experiments were the same for all transmission types. And efficiency versus load graph, the difference between real and ideal input weights. And also cycloidal drive. Cycloidal drives are used in heavy machinery and robotics due to their compact and relatively well performance. The cycloidal drive consists of 5 main components: input shaft, eccentric cam, cycloidal disc, and ring gear, and an output shaft. So let's see the most interesting aspect of this transmission, which is a cycloidal disc. Cycloidal disc gets its shape from an epicycloid curve, which is basically a point on a circumference of a circle that revolves around a bigger circle. And also the motion. As the disc is located on an eccentric cam, movement of the eccentric cam forces the disc to move in an orbital-like motion. And here is the reduction ratio. And my setup consists of two cycloidal discs with 9 lobes, input shaft, casing with 10 rollers, output shaft, 4 bearings and 2 pulleys, and the reduction ratio is 10. As you can see, I use two cycloidal discs. It is because when using a single disc cycloidal disc, there are a lot of vibrations in the system that reduce reliability of the drive overall. When two discs are placed at 180 degrees apart, the forces cancel out and leading to reducing vibration and improving the overall reliability of the drive. Here you can see the real build, also the ideal case simulation that we did. The negative sign on the output just shows that the output revolves, the direction is negative, opposite of the one of the input. Then the table that every student will have to fill: efficiency versus the load graph, difference between real and input weights. But apart from developing these three transmission units, I also developed user manuals for each, and they include detailed explanation of the theory, steps of experiment procedures, and post-experiment questions to see if the student grasped the idea of the transmission unit. The future work would include new transmission experiments and also combination of few experiments into one, meaning few drives together. And to conclude, I would also like to acknowledge a few people. First and foremost, Professor Sarkis Zeytunyan for being an exceptional capstone supervisor and for his constant guidance, support, and belief. Arman Asatryan for always being ready to help and share his experience with me. Mariam, our TA, for guiding and supporting us through the capstone project, and my course mates and friends for amazing 4 years in the university. Thank you.
Did you consider to put this in a cutout model to be more,
I was
because it's an education project and cutout model, like especially more complex model like this, would be helpful.
So yes, the design was made in such a way that students can actually see when how the motion is transferred through these cutouts. But the cycloidal drive, as I said, it is different kind of transmission, and it is much more compact, but also it needs a lot of structural rigidity. So I decided to close everything so the structural rigidity is good, so the students will learn and know that it is needed like this.
Yeah. And what about the educational materials?
The user manuals or
No, I mean, it is an educational project for the other students to get involved or get interested.
yeah, this is made so students, as I said, the robotics is getting much more involved into machinery or overall our life, and there is high need of people who know how to design, how to calculate everything about the transmission, so the need can be filled, and this with also Edibon setup will fill that gap of the people who actually learn. Students will, as these components, these drives can be integrated into different courses to learn how they model. For instance, they can be incorporated to CAD to learn how to model dynamics, to learn how their motion is going, and also, for instance, mechatronics to learn how to implement them actually.
Comment from my supervisor.
Just I want to mention very consistent, very good work from her, and I want to mention that he was just a kind of emergency person in the lab, and majority of students who presented here on prototyping design related projects, I think in their acknowledgement should have mentioned also in Mher Baburyan. He is a volunteer proctor in our lab.